Hi, today I will give you an example of dimension analysis. Dimension analysis is especially useful if you have a process or a situation where you have a lot of variables and you can reduce them to a few dimensionless groups. Today I give you an example of a problem with not too many variables in it. Let's say the problem is as follows. We have a ceiling, and on this ceiling a droplet is formed. And this droplet is growing. And at a certain moment the droplet is grown to a critical volume, and this critical volume drops down onto the ground. And dimension analysis, you can say, where is this critical volume dependent on? Well, first of all, the gravity constant will be a variable which will be in this case relevant. Another one is a property of this droplet. Well, let's say there's water. It should be, let's say, the density, which is really important. And last but not least, why is the droplet staying on the ceiling? Because the surface tension is a really important parameter. So in this case, you could say that the critical volume is a function of the gravity, the density, and the surface tension. Now dimension analysis states that this critical volume can be written as a constant multiplied by the gravity constant to the power A, multiplied by the density to the power B, and to the surface tension to the power C. Now we have a relation between left and the right side, and the principle is that you now look at the dimensions. So what we now write down is the SI units of each of these properties. Well, the volume has the dimensions of cubic meters. A constant is dimensionless. This is meters per second squared to the power A. This is the density, which is kilograms per cubic meter to the power B. And the surface tension is joules per square meter, but you can rewrite this in SI units till kilograms per second squared to the power C. Now you have to look at this relation. The dimensions left and the dimensions on the right side should be equivalent. So if you now write down three equations, let's say in the kilograms, you could say, well, on this side there are no kilograms, so 0 is equal to. Now we look at the right side and we see that we see B and we see plus C. The similar what we're doing is with meters. We look at this side, we see a 3 is equal to A minus 3B. And in this case we don't see any meters. And the last equation is the seconds. There are no seconds on this side. 0 is equal to minus 2A. Here we don't see any seconds, and here the last is minus 2C. Well, if you combine this, you have now three equations with three unknown. Well, sometimes you have many more variables, so with only three equations, so you get more dimensionless groups. But in this case, in principle, you can solve the whole problem, because you can now derive a value of A out of this. If you do this, you get the following. You could say, if you derive it in the right way, you get A, in this case, is minus 3 to the point 2. You get B is equal to A, and C is equal to minus A. And if you rewrite, you substitute it in this equation, you get the following dimensionless group: critical divided by the density, the gravity constant, and the surface tension till the power 2 is constant. I have now made a fast step, but what you see here, this is a dimensionless group which is constant. And this is in principle the principle of dimension analysis. Now we have one group, but normally we have many other groups like Sherwood numbers, Nusselt numbers, etc. Try to work out this example and try to get the feeling about dimension analysis. Thanks for looking at this movie.